Chapter 4, Equipment Quality Control in Spirometry. So in Chapter 4, what we're going to learn about is quality control, environmental conditions, ATPS to BTPS conversion, equipment maintenance, care of the calibration syringe, mechanical calibration, and biological quality control. After studying this chapter, you should be able to define and explain quality control in spirometry, explain how to check and care for the calibration syringe, explain the effect of environmental conditions on the measurement of spirometry, understand and assess ATPS to BTPS conversion, conduct a linearity calibration check on a spirometer and assess the result as valid or invalid, describe and conduct characterization for biological quality control, and describe and conduct a biological quality control check. So what is quality control then in spirometry? Quality control refers specifically to spirometry equipment checks that ensure that the spirometer is reading accurately prior to testing, and quality control is part of quality assurance. So quality control procedures must be applied on a routine basis. Device quality control minimum requirements are as follows: care of the calibration syringe, mechanical calibration, and biological calibration, those three things. And we're going to look at them now one by one. So first of all, what do we need? What equipment do we need to conduct a quality control check? Obviously, you need your spirometer, and the spirometers come in various measuring and operating principles. It's important that you read your manual and you understand how your spirometer actually works so that you can understand the ins and outs of calibration checks specific to your spirometer itself. You will need a weather meter, a little digital device that measures ambient temperature, pressure, and humidity, because we need to understand that the conditions in the room are different to the conditions in the chest when the air is expelled from the patient in a spirometry test itself. You will need various disposables. You will need things like bacterial filters, disposable mouthpieces, and anything else that a child would use when they are actually blowing onto the machine. So when you do a calibration check, you need to attach every part or connector, bacterial filter, and mouthpiece to the spirometer that you will be using when the child is actually blowing on the machine during the test. You will need various adapters and connectors, and I brought a few with me just to show you that if you don't have the correct adapters or connectors, you're really going to be in a fix, because you won't be able to attach your calibration syringe the way you would like to your spirometer. You've got to be sure that when you're calibrating, the connection between the syringe and the spirometer is absolutely airtight and that there's no leaks. Right, let's look at our calibration syringe and how to care for the calibration syringe. So a calibration syringe is a 3-liter syringe, which is the gold standard. They do come in 1 and 2 liters as well. But really what we're wanting here is for you to understand that this is a piece of equipment in its own right, and that we need to make sure that this syringe is in good working order before we use it to actually conduct a calibration check on the device itself. Every calibration is identifiable by a serial number, which can be found on the syringe somewhere. And over time, wear and tear can cause this syringe to have various issues which could change the performance of the calibration check. And that's what I'm going to help you to look at now. So the first thing you would do to care for your syringe and understand that it's in good working order is to do a visual inspection. A visual inspection is just to make sure that there's no cracks in the housing, there's no lost screws, that there's nothing blocking the outlet port, and that the little baffles that actually are put in place to measure the volume of air in the syringe are tight and firm. The next thing you would do is a syringe leak test. And a syringe leak test is really making sure that the seals inside the plunger are not broken in any way. So you would occlude the outlet port, push down on your handle as hard as you can, and if there's no give, there's no leak. If there's a little bit of a give, there's a leak. Third thing is that you want to do a syringe smoothness check. So that is just moving the plunger in and out of the syringe to make sure that it is moving freely, that there's no stickiness. That's going to result in problems when you're calibrating the machine itself. And lastly, we would be looking for a calibration verification check. So on a regular basis, sometimes annually, we would want to be getting a certificate whereby the manufacturer of the syringe or a designated party has checked the syringe and knows that it is reading the volume accurately. And we know that a syringe volume is reading accurately when it has a volume of within 0.5% of the syringe volume. And in the case of a 3-liter syringe, that's 15 milliliters. If you look at figure 4.9, I've given you two different scenarios of a calibration check done with a smooth syringe. That's the top graph, flow volume and volume time graph. And then just below that, you can see a calibration check done with a sticky syringe. So we want to make sure that our calibration syringe is well cared for and that it's in good working order before we use it on a spirometer to make sure that it is working correctly. Let's look at a factory calibration. What is factory calibration? That is the calibration that is conducted on the machine in the factory before that machine gets sent out into the workplace. And we would term that the baseline calibration. So every time we do a calibration check, we're not resetting anything in our spirometer. All we're doing is checking that the volume of air measured at the time of the calibration is within 3% of that baseline factory calibration. So as long as the volume measured at the time of calibration is within 3% of the baseline calibration, we can say that the spirometer is reading volume accurately. Let's look at what a volume calibration check is then versus a linearity test. So a volume calibration check very simply is conducting a calibration check on a device using any syringe stroke. So it doesn't matter how fast or how slowly you actually move the syringe plunger, it's all about the volume of air measured at the time of calibration. I'm going to show you how to do a volume calibration check in the practical sessions. So if you would like to halt at this point and go to the practical session, go and have a look at how a volume calibration check is done, and then come back and let's carry on. Okay, so what is the difference between a volume calibration and a linearity check? So a linearity check takes things one step further. It looks at the volume of air measured at different flow rates. So a volume calibration very simply is looking at the volume of air pumped onto the spirometer and making sure that the measured volume on the spirometer is within 3% of the syringe volume. Whereas a linearity check is making sure that the volume of air read by the spirometer at the time of calibration is within 3% of the syringe volume at different flow rates. So in a linearity check, you need to pump the air onto the spirometer at low, medium, and high flow rates to look at the volume of air measured at any flow. And the reason why we do this is that you have different size people with different lung volumes and different flow rates blowing onto your spirometer at different times. We want to make sure that the volume of air measured in any patient, no matter how small or tall they are, how young or old they are, whether they're male or female, we want to make sure that the machine is reading volume accurately across any flow rate so that we know that we're covering all patients when we measure volumes. If you look at figure 4.11, you will see an example of a volume calibration procedure. And if you look at the actual final measurements, you will see that we are only interested in looking at the volume of air measured. That is your FVC measurement. If you look at figure 4.12, you will also see a volume calibration check procedure where all we would look at is the FVCs and the FIVCs and check those against the syringe volume to make sure that the volume of air being read is within 3% of the syringe volume. When you look at a linearity calibration check, we now need to move the syringe plunger at different flow rates. We need to move it at a low flow, a medium flow, and a very high flow. A low flow in linearity checking is moving your syringe plunger at less than 1 liter per second. A medium flow is between approximately 1 to 2 liters per second, and high flow is anything above 6 liters per second. And once again, you need to go to the practical session on linearity testing to see how a practical linearity check is carried out. By doing a linearity calibration check, we can see that the volume is measured correctly at low, medium, and high flow rates, proving that the measurements of volume and flow rates of any size person with any size of lung volume will be measured accurately. If you look at figure 4.13, this shows a single flow calibration check. What that means is that the syringe plunger was only moved once in and once out again, and we have looked at the volume measured at that moment. In figure 4.14, you will see a linearity calibration check. There you will see 3 very distinct flow rates, expiratory and inspiratory, and the syringe has been moved at low flow, at medium flow, and at high flow. And then we look at the FVC measurements and the FIVC measurements to ensure that those are within 3% of the syringe volume itself. So a calibration check is valid if the volume falls within plus or minus 3% deviation of the syringe volume, regardless of the flow rates. A linearity check is valid if the volume falls within plus or minus 3% volume deviation at low flow, medium flow, and high flow. If the flow rates are not within acceptable ranges, then we would want to try and redo the calibration check again to be sure that we've checked volume across the flow ranges, low, medium, and high. In figure 4.15, you'll see a linearity calibration report. And if you look very carefully, you will see that I've shown you 6 very clear steps to looking at the report of any calibration done on any spirometer. First and foremost, you will look at the date and time to be sure that this has been correctly documented. In the green, in number 2, you'll look at the ambient conditions recorded at the time of calibration. And what you'll see there is that we have recommended ranges for temperature, pressure, and humidity. The temperature should be within 17 to 35 degrees Celsius. The barometric pressure within 450 to 825 millimeters of mercury, or 600 to 1,100 hectopascals, depending on the unit of measurement that you're using. And the relative humidity should be between 30 to 75%. If they are outside of these ranges, you would have to make a note on the report so that anyone who is then assessing the calibration report or the spirometry report at a later time would be able to make mental calculations of how that can affect the actual test result itself. Step number 3 would be looking at the measured volumes against the syringe volumes, and that is shown very clearly in the red writing. You can see that the measured volumes must fall within 3% of the syringe volume, and when using a 3-liter syringe, that's 90 mils of 3 liters. So you're allowed a range of 2.91 liters to 3.09 liters. For those values to be measured, the measured values must be within 2.91 to 3.09 liters at any flow rate. Fourthly, you would want to look at the flow rates and make sure that the correct flow rates have been used for low, medium, and high flow. So you can see on the graphs very clearly where we've documented low, medium, and high flow. And in linearity, it's very, very important that you learn to pump that syringe handle at the different flow rates so that we can measure volume across the range. Step number 5 is writing a validity statement, and this is often where the understanding comes of calibration itself. So what you want to say is whether the linearity check is valid or invalid. A linearity check is valid if the volume of air measured is within 3% of the syringe volume at low, medium, and high flow rates. And then lastly, step number 6, you need to sign and date your report. You can see that in figure 4.16, there's another calibration report done on a different spirometer, and you should follow the exact same 6 steps to find out if this is a valid linearity check. And you can see again that they are very clearly labeled. Yellow, step number 1, check your date and time. Step number 2, check your ambient conditions at the time of calibration. Step number 3, look at your measured volumes versus your syringe volume. Step number 4, look at your flow rates to make sure that you used a low, medium, and high flow. Step number 5 is understanding whether or not this is valid and writing a statement on that. And step number 6 is signing and dating. So if you follow those 6 steps, you should never be lost in terms of reporting on any calibration report at any stage. When should you do calibration checks? So the ATS ERS guidelines for calibration state that for spirometry, calibration or verification should take place every day in normal departments and at least twice a day in busy departments. So calibration verification should not be done necessarily between tests. You don't have to do this before each new patient. You need to do it at regular points during the day or at least daily before the first patient of the day. Another time that you might want to consider redoing your calibration check is when the ambient conditions change in temperature by more than 3 degrees in 30 minutes. So if your temperature is fluctuating a lot, it's a good idea to make sure that you are rechecking the calibration of the machine. And the reason for this is that the volume of air measured in different temperature pressures and humidities will read the volume differently when the patient is actually blowing. So we need to make an adjustment on that and a little bit more on that later. Let's look quickly at the common problems when calibrating the spirometer and how to manage these. So one of the first things is that there could be a change in the spirometer function that requires a subsequent recalibration procedure to adjust the calibration factor. Now, what you should do is check that all the components and parts for leak or damage, and then repeat the calibration procedure again. Next, look for a leak in the connection of the spirometer to the calibration syringe, and that's where all these little connectors become important, because we want to make sure that the syringe is level and snugly attached to the filter or mouthpiece using the correct connectors. A very important part of calibration is making sure that there is no air flowing through the spirometer immediately before the calibration check takes place. So the spirometer is set up to measure baseline airflow. What that means is that there's no flow of air at the time that you start the calibration. And the reason for this is that if the baseline airflow is not measured correctly, then the amount of air that you are looking at when you are calibrating the machine will also not be measured correctly. One of the things that people do wrong when they are calibrating the machine itself is that they don't pull out the syringe plunger all the way, and they might not put it all the way in. If you leave a little gap like that, obviously the volume that you're measuring is going to be incorrect. So make sure when you're using the syringe handle that you're pushing it all the way in and out. Sometimes a calibration syringe can malfunction, so there could be a problem with the piston leaking, displacement of the stopper, or the syringe could be damaged by dropping. So if the syringe does somehow manage to get dropped, it does happen at times, the first thing you're going to do is recheck the calibration of the spirometer before you use it on a patient. And if necessary, you may have to get the syringe repaired before you can go forward again. Sometimes the spirometer is blocked by debris, so the spirometer sensor, the operator's hand, can be in front of it at the time of calibration, and just be very careful of that as well. You want free-flowing air, so nothing should be occluding it when you're actually doing the calibration itself. Sometimes people assemble the equipment incorrectly, so check your manual very carefully for how your spirometer equipment needs to be assembled. Sometimes the differences between the room temperature and the calibration syringe temperature are such that it can make a difference when measuring the volume of the air. So if you leave this syringe under a direct source of heat, for example, under a window where the sunlight is streaming in directly onto it, or under an air conditioner where it's getting very cold, then the volume of air in the syringe could be different to the volume of air outside of the syringe, and that may not be corrected. So always store your syringe together with your spirometer in a place that is not particularly too hot or too cold area of the room, like under a window or under an air conditioner. Spirometry measures the volume of air the lungs can hold and the flow of air through the airway. So volume and flow measured at ambient conditions, that's ambient temperature, pressure, and humidity, differs to the volume of flow measured at body conditions. So we need to make an adjustment for that. So you do understand then that when a child blows into the spirometer, the air expired from the lungs is moist and warm straight from the body. Inspired air is drier and cooler and expands in the lungs as it becomes heated. So inspired air must be converted to be body temperature, pressure, and humidity, or fully saturated with water vapor, for the measurement to take place accurately. So the body temperature, pressure saturated with water vapor conversion differs on inspiration and expiration and is calculated by the software of the spirometer based on the ambient conditions entered into the spirometry software at the time of calibration. And you can see a demonstration of this on the practical linearity check. Let's look at ambient temperature. Let's look at how temperature affects the volume of air measured and what corrections we need to make at the time of calibration. So the ambient temperature should never assume to be constant. It should be measured regularly and entered into the spirometer software within plus or minus 1 degree Celsius. So if the ambient conditions are changing rapidly, so in other words, if you're not in a weather controlled room, in other words, you're not working in an environment where you have, for example, an air conditioner, you can have big swings in temperature. So from the morning, it could be, for example, 18 degrees Celsius, and by lunchtime, it could be 25 degrees Celsius. We want to make sure that there are corrections for that when the patient actually blows onto the machine. So if there's more than 3 degrees Celsius change in temperature within 30 minutes, then you may need to recalibrate your machine if there is not a facility in the spirometer itself to measure continuous temperature corrections before each and every blow. Correction factors for temperature are usually in the range of approximately 8 to 12%. So if temperature and humidity are high in the environment, then the correction factor decreases. And if inspired temperature and humidity are the same as the temperature and humidity in the lungs, then no correction is required. If you look at figure 4.17, you can see a graph that shows error calculated in the BTPS factor when the ambient temperature entered into the software of the spirometer is different to what it really is in the environment itself. So if you look at the x-axis, you're looking at the actual temperature in degrees Celsius. And if you look at the y-axis, you're looking at the error in the BTPS factor as a percentage. So for example, if the ambient temperature is 22 degrees Celsius, there will be no percentage error in the volume of air measured. But you can see then how this changes on a sliding scale. If the ambient temperature is 30 degrees Celsius, that will give you 4% difference in the measured volume of air, and the same in the negative. So if it is 12 degrees Celsius, you will see that there will be a minus 4% measurement of volume of air. So it's very important with temperature especially that we enter the correct temperature from the ambient conditions at the time of calibrations so that a conversion can be made to accept a patient who is blowing with body temperature, pressure, and humidity. Remember that when you move your spirometer to a new location, you should really look at the temperature each and every time you get to a new place. And therefore, we can make the adjustment easily if we make these corrections for ATPS to BTPS every time we do a calibration itself. And remember, it's important to keep the syringe and the spirometer stored together in the same place. Barometric pressure changes are far less severe than temperature changes. So an altitude change of 1,000 meters changes the correction factor by only 0.7%. Not as dramatic as a temperature difference, but something we still need to take into account anyway. And if you look at figures 4.18 and 4.19, you can see graphs showing error when barometric pressure is entered into the software of the spirometer differently to what it is at the time of calibration, or when some people just assume what the barometric pressure is. You can see that there can be quite a wide swing in how volume is measured, but nothing as dramatic as the temperature. Look at figure 4.20 to get a sense of how the relative humidity at the time of calibration differs when a patient blows into the machine itself. So again, also not as severe as the differences in ambient temperature, but nevertheless significant enough for us to pay attention to measuring and entering our temperature, our humidity, and our pressure when we are calibrating a machine. So just to recap then, the ideal ambient conditions for spirometry are an ambient temperature of 17 to 35 degrees Celsius, a relative humidity of 30 to 75%, and an ambient pressure of 600 to 1,100 hectopascals or 450 to 825 millimeters of mercury. And then occasionally some people do measure in kilopascals, and your ranges allowed would be 60 to 110 kilopascals. So when it comes to recording and reporting and keeping records of your calibration checks, you need to be sure that you have a computerized date and time displaying correctly on the calibration report itself. The ambient conditions in the room at the time of calibration should be noted somewhere on the report. You need to make sure that all the measured volumes fall within 3% of the syringe volume that you are using. You need to make sure that if you're doing a linearity check, that you used low, medium, and high flow rates. You need to know whether or not your calibration is valid and to make an intelligent statement on that when you report on your test result itself. And then you need to sign and date. So all calibration data should be stored in the spirometry software. There is a log where you should be able to go back in the software and pick out any calibration report at any time to match it up to a relevant spirometry test that you might have conducted. If for some reason your spirometer is printing on thermal paper, remember that thermal paper fades over time. You would need to copy the original calibration report to a normal A4 paper and then store the two of them together in your files or wherever necessary. What will happen if accuracy and precision of the spirometer is not maintained? If an inaccurate or imprecise spirometer is used to measure a child's lung function, the results may show a false negative or a false positive result, and we don't want to do that because spirometry tests are used to make decisions such as treatment initiation, discontinuation, employment for certain roles, disability compensations, etc. And the consequences of making an incorrect reading could be dramatic on any individual's life, whether it is a child or an adult. So in summary on spirometry calibration, mechanical calibration, that's using a syringe to calibrate, a daily calibration verification check should be carried out with the syringe pumped at low, medium, and high flow rates, meaning you're doing a linearity check. A volume calibration is not enough anymore. We want to look at the volume at different flow rates. If an inline filter is being used, that's a bacterial filter, whilst you are doing a spirometry test, then you must connect that into the circuit when you are calibrating. Recalibration of the spirometer after a failed calibration verification is recommended. So if your calibration fails the first time, that's not a problem. You keep trying to calibrate. If for some reason the machine does not want to fall within a valid calibration, you would then have to be in touch with the manufacturer and ask someone to come and have a look at your spirometer itself. And then in time, if the change in calibration factor is equal to or greater than 6% or varies by more than 2 standard deviations from the mean, you need to inspect and, if necessary, clean the spirometer according to the manufacturer's instructions. You need to check for errors and recalibrate the spirometer itself. You could perform routine calibration checks at maintenance at intervals specified by the manufacturer. So, 3-liter calibration syringe, you do daily inspections for the actual piston stop itself. Make sure that the little baffles at the end of the syringe are not loose. Do a smoothness check, do a leak test, and be sure that your machine is verified and certified, reading within plus or minus 15 mils on a 3-liter syringe, which is 0.5%. Keep all your documentation in your spirometry software itself or in your paper files, whichever way you do it in your workplace itself. So now I want you to go on to activity 5, where you will conduct a volume calibration check yourself, and then you will also conduct a linearity check yourself. Let's look now at biological quality control. So as part of an ongoing quality control program and to detect changes in the overall spirometer performance, the lung function of someone readily available and healthy with a stable and normal lung function should be measured and recorded. So this person that we use as a biological quality control is usually the spirometry technician themselves. But this person must not smoke, must have no respiratory disease, they must be completely healthy and capable of performing repeatable spirometry on a regular basis. And it's very important that we do the biological control testing at the same time of day to minimize the effects of circadian rhythms and differences in lung function from morning to evening when we are doing biological calibration itself. So to do a biological calibration, what we need to do is what we call characterization. And that is finding out what are the normal ranges of volume for the specific biological quality control person. And the way we do this is we get the person to blow onto the machine every day for at least 10 days over a 2-week period. So from a Monday to a Friday, 1 week, and then the second week a Monday to a Friday, this biological quality control person should blow onto the machine every day at the same time of day to be sure that they are measuring so that we can get the ranges allowed for them. So every test that has been conducted should be recorded and possibly printed, either a digital printout or a paper printout, where the highest values for each spirometer are then recorded and looked at as a whole. So the mean value for each parameter is calculated by adding all the 10 tests together and then finding out what is the mean for this person at this time. So we would then use this answer, the mean average FEC and the mean average FEV1, to use as ranges for someone to blow in time to come. So what you would do, if you look at the next slide, is you would look at 10 FECs and 10 FEV1s have been conducted. We have extracted the data from the spirometry software program onto a spreadsheet of some sort. We have calculated what the average mean is. And in this example, the average mean FEC is 3.63. By adding up all the tests day 1 to 10, you have got an overall of 36.25 liters divided by 10 gives you 3.63 liters. And then to get a range allowed, we subtract 5%, we add 5. And when we do this, we know that the FEC range allowed for this biological control is 3.45 to 3.81 liters. We do exactly the same thing with the FEV1. We take 10 measurements over 10 days, we add them together, we get a total value of 30.74. We divide by 10 to get an average of 3.07. We add and subtract 5% to give us 2.92 to 3.22 liters. So the reference range for this person, this biological quality control person, would be an FEV1 of 2.92 to 3.22 and an FVC of 3.45 to 3.81. Now, thereafter, every week, once a week, this person will blow onto the spirometer, and if the FVC and FEV1 falls within those allowed reference ranges, we know that the machine is reading accurately. So I would like you to do the exercise now, activity 6, whereby you will find an empty biological calibration chart followed by 10 spirometry tests conducted on a control person. You need to use those 10 spirometry printouts to extract the FVC and the FEV1, the best FVC and the best FEV1 for each of the days that the person has blown. Work out what is the mean for the FVC and the mean for the FEV1, and then add and subtract 5% to each of those to get your ranges for that biological quality control person. And that brings us to the end of calibration. So what you will see in the slides to come is that there are various calibration examples that we have used for you to work on, where you apply your 10 steps to checking your calibration. So on each and every one of these example calibration reports, you could look to find the date and time, the ambient conditions, the measured volumes with the syringe volume. Is it within 3%? You could look at your flow rates to see that you've got low, medium, and high flow rates, make a validity statement, and then sign and date your calibration report. A few little did you knows, some interesting facts about calibration. When reading your weather meter, you should check that the units of measurement requested by the spirometer are the same as being read from the weather meter so as to avoid errors. What can happen is that the weather meter may give you the ambient conditions in hectopascals, but the spirometer might ask for the answers in millimeters of mercury. So be careful to check for that. When you are getting consistently high results from different subjects, you should check your quality control procedures to be sure that the equipment is not malfunctioning. Biological calibration should not be used as a substitute for mechanical calibration. They are entirely different procedures. A mechanical calibration is mandatory. You have to do it on a daily basis, whereas a biological calibration procedure is recommended, but it is not mandated. You can choose whether you want to do it or not. A good quality spirometer is essential for reliable results. And lastly, the 2019 ATS ERS technical specifications for spirometers must be met. So you need to be using a really good quality spirometer to ensure that you get good quality results on your patients. Choosing a spirometer that can display large screenshots of the flow volume and volume time curves is really useful in spirometry to see what is actually happening at the time of calibration and testing itself. Pneumatic spirometers, if you have one, some people don't know that you need to leave them to heat up for 15 minutes before you start to test using them. And the performance of some spirometers can be really affected by extremes of temperature, pressure, and humidity. So always store your calibration syringe with your spirometer away from heat, away from cold, just in the center of the room where ambient conditions are as stable as possible. Thank you very much, and we will speak soon now on Chapter 5.